we've made this definition of vector spaces. A vector space is a collection of vectors, a choice of scalars, and then two operations, vector addition and scalar multiplication, that satisfy this big list of properties. But what are some vector spaces? Well, since this definition was inspired by the collection of vectors Rn, that is the collection of column vectors with n real entries, it had better be the case that Rn is a genuine vector space. So I guess just check. Well, really we have checked all these properties for Rn to begin with. That's really what inspired the list of all of these properties. So there's really not much to check here. But Rn really is sort of the archetypical vector space. Usually if we think of a vector space and if we are just thinking about vector spaces in general, Rn is usually what we picture just because Rn is so familiar. So is Rn a vector space? Yeah, of course. We made the definition of a vector space basically specifically so that Rn would be a vector space. But the term vector space, one thing you have to get out of the habit of thinking is that the term vector space refers to something, I guess I should say the term vector. You should get out of the habit of thinking that the term vector refers to something like this, a column or row or list of numbers. That isn't always the case. So let's look at some examples of other vector spaces. So one good example of a vector space is the collection of all m by n matrices. So we're going to call this capital M subscript m comma n. So mmn. This is the collection of all m by n matrices with real entries. So is this a vector space? Well, if you have two matrices of the same size, so maybe let me call it V11, V12. Let's look at an example that's 2 by 3, just to have something concrete. V13, and then V21, V22, V23. What would it mean to add two matrices? Well, if they have the same size, so let me call this one W. If they have the same size, you can kind of guess how it makes sense to add matrices. You should just add corresponding entries, right? So this is going to be V11 plus W11, that's a W, and so on, all the way down to V23 plus W23. Okay. Clearly, this is inspired by the vector operations on Rn, where you add corresponding entries. It's the same thing here. We just have to make sure that our matrices are the same size so that there are always corresponding entries to add together. By the same token, scalar multiplication for this collection mmn will just be multiplying each entry by the scalar. So R times V11 down to R times V23 for this example. Okay, so that defines the collection of vectors. Notice in this case what we're calling vectors are really matrices. So you know what the word vector means is very context dependent. A vector is just something in your vector space. They might be genuine vectors, but they might be matrices, or as we'll see, they might be other types of things entirely. We've made a choice of scalars because we said we're going to use R. We'll always use the real numbers. We have operations. So now we need to check all of these. So are these closed under addition? Well, clearly, because the sizes match up, you can always add matrices of matching sizes to get another matrix of the same size. So addition is closed. Commutativity is clearly satisfied because we're just adding things entry by entry. And so when it comes down to it, really we're just asking about the commutativity of real addition, but that is commutative. Same thing for associativity. For an additive identity, well, remember an additive identity, that's just a fancy word for something that acts like 0 for this vector addition. And of course the matrix with all 0 entries is going to be our additive identity. So we have an additive identity. And how about additive inverses? Well, you know, additive inverses, those are fancy words for negatives, or if you just throw a minus, if you have a matrix and you want its additive inverse, just throw a minus sign on all of the entries, right? And that's going to give you additive inverses. So scalar multiplication, clearly closed. Associativity, yeah, not much to check here, right? All of these things are pretty clear. And then scalar multiplication over vector addition and scalar multiplication over scalar addition, again, those come down to, because these operations are defined entry by entry, both of these come down to real distribution over real addition, so both of these are satisfied. So the collection of matrices is a vector space, even though it's full of matrices and not what you might think of as vectors. Let's look at another example. So how about the collection of all polynomials of degree n? Now, matrices might seem, saying that a collection of matrices is a vector space might seem like cheating, because after all, a matrix is just a bunch of numbers. The fact that they're arranged in a rectangle, like a matrix, instead of a column, like a vector, doesn't really make all that much difference as far as the vector space axioms here go. But polynomials are genuinely different things. Right? A polynomial is not just a list of numbers. A polynomial is it has a variable, it represents a function, it has a graph, right? So a polynomial is a genuinely different thing. But at the same time, we can still ask, does the collection of polynomials of degree n satisfy all of these properties? If so, then it's a vector space. If not, then it's not. So let's check. So we definitely have a collection of vectors, right? The collection of all of the polynomials of degree n. And we have a choice of scalars, because as usual, we're going to stick to real numbers. Polynomials come with their own sense of addition and multiplication by a real number, because polynomials are functions, and we already know how to add functions and multiply them by constants. So now we can ask about all of these properties. So if you have, so just to be concrete, let's say we're asking about p sub 3, so polynomials of degree 3. So is addition, is polynomial addition closed under, right, is polynomial addition closed for p3? Well, it seems like it, right? If you have one polynomial of degree 3 and you add to it another polynomial of degree 3, I don't know, something like this, do you get yet another polynomial of degree 3? Well, in this example, yes. But remember, we have to think about every possible two polynomials that we add together. So let's see, are there any ways that we could add two polynomials together and get a polynomial that is not of degree 3? So add two polynomials of degree 3 and get a polynomial that's not of degree 3. Well, yeah, that is possible. We could add x cubed plus x to negative x cubed, right? These are both polynomials of degree 3, but when we add them together, we don't get a polynomial of degree 3. Instead, we get a polynomial of degree 1. So this is actually not a vector space. It's not closed under addition. Okay, well, that's kind of disappointing. But how could we fix this? Clearly, the mistake that we made here when we made this definition is that we insisted the degree be exactly n. So let's change our definition, right? Forget all of this. And instead of having the polynomials of exactly degree n, let's have the polynomials of degree less than or equal to n. So of degree less than or equal to n. Okay, so still we have, we've chosen a collection of polynomials, which are going to serve as vectors. We have scalars. We still have polynomial addition and multiplication, scalar multiplication for our operations. So now let's ask again about closure under addition. If you add two polynomials of degree, say, 3, do you get a polynomial of degree 3 or less? Well, yes. I mean, when you add two polynomials, you always get another polynomial, so the only question is about degree. But when you add two polynomials, the resulting degree can't be any bigger than the two that you started with. So if you start with two polynomials of degree less than or equal to n, their sum is going to have degree less than or equal to n. So this time, closure is satisfied. So we have some hope of having a vector space. Commutativity of addition, well, that's clear. We know that from knowing stuff about polynomials already. Same thing for associativity. Additive identity is clear. That's just the 0 polynomial. Existence of additive inverses, also clear. That's just the negative of a polynomial. And then, right, all of these properties for scalar multiplication, these all follow from the fact that scalar multiplication for polynomials is just real multiplication, essentially. So this collection of polynomials of degree less than or equal to n is a vector space, even though it's made up of things that are not actually vectors. They're polynomials, but they act enough like vectors that we will be able to do linear algebra with them. All right, let's look at a couple more examples of vector spaces. So how about the collection of all of the functions from any set to R? So this is one way of writing that collection. So this is just the collection of all functions from S to R. Okay, so we've defined a set. Whether it makes sense to call it a set of vectors has yet to be determined. For scalars, of course, we're going to use R still. We need to define addition and scalar multiplication operations on this set. So what we can do is, to decide what the sum of two things is. Well, the sum of two things, we're hoping it's a function from S to R. So to tell you what function it is, I have to tell you what happens if you evaluate it at any given little s in big S. Well, we can just add things pointwise. So f is a function defined on S, so put our little s into f, put little s into g, and then just add the results. Right? So to add two functions, you just add them pointwise. Same thing for scalar multiplication. If we have a scalar times one of these functions, what function is this? Well, to tell you what function it is, I have to tell you what comes out if you put s into it. And what comes out is r times f of s. So this defines these operations. Now we just have to check all this huge list of axioms. So closure under addition is clear this time, because if you have two functions, when you add their outputs, you just get another function, right? We're familiar enough with adding functions that there's not much to show there. Commutativity of addition, well, to know if this addition operation we defined is commutative, we have to look at its definition. And how we defined it is with this addition right here. So we have to ask, is this addition commutative? Well, this addition, what is being added here? What are the outputs for these functions? Well, the outputs of these functions are real numbers, because this function is from some set to real numbers. So this addition is real addition, right? It's real number addition. And real number addition is commutative, so we get commutativity. Same thing for associativity. For an additive identity, maybe this one isn't as obvious to see. What function would you have to add to some mystery function f so that you get the same thing as just f? Well, right. So I'm asking, what goes here? Well, we're hoping that we get a function that's equal to just f. So whatever this is, it had better be 0 all the time. But of course, that's what counts as the 0 function. It's the function that is just always 0. So our additive identity is the 0 function, which I don't really want to write it as 0, so maybe we could write it with a z. The function z, which is just always 0. For additive inverses, you can tell you're just going to stick a minus sign on your function, and then on every output of your function, and then you have additive inverses. For properties of scalar multiplication, right, this multiplication right here that we're using to define scalar multiplication is actually just multiplication of real numbers again, because the outputs of our functions are real numbers. So we get all of these properties for free, and same thing for these. So any collection of functions from a set to real numbers is a vector space. Often we will, when the examples of these kinds of vector spaces come up, this domain set here is actually also real numbers. So, you know, a big example of this is just all of the functions from the real numbers to the real numbers. Altogether, those form a vector space. Or all of the functions from the positive real numbers to the real numbers. Those also form a vector space. So you can see this is a easy way to get vector spaces. The final example of a vector space that I want to look at is, right, all of the ones we've seen so far are kind of more on the symbolic or algebraic kind of side of things. But if you've seen vectors before, you might have drawn them as little arrows in the plane. I mean this to say plane. Little arrows in the plane, or maybe in 3D space. Well, let's make that concrete by actually checking that geometric arrows in a plane do form a vector space. I'm going to insist that our vectors start at the origin, and of course for scalars we're going to use the real numbers. So first I have to tell you, how do you add vectors in the plane? Well, here's the origin, and here are two vectors. To add them, we're just going to lay them head to tail. So, right, if this one is v and this one is w, what we're going to do to get v plus w is slide w over so that it is starting where v ends, and then we're going to go from the origin, the beginning of v, over to the end of w, like this. And this is v plus w. Okay, so that's a definition of vector addition. For our scalar product, we're just going to use r as a scaling factor. So for example, if this is v, then 2v, right, the scalar 2 times the vector v is the same vector but just stretched, so it's twice as long. Minus 1 times v is going to be, let me put it over here, minus 1 times v is the same vector but in the opposite direction. Right? So for our scalar multiplication, we're just going to scale the vectors. That's why they're called scalars, because geometrically we think of them as stretching vectors. Okay, well, with these definitions, now we have to check that big list of vector axioms to see if we have a genuine vector space. Well, clearly if we lay vectors head to tail, we're going to get another vector, so this addition is definitely closed. To see that it's commutative, well, here I've slid w over to the end of v, and we get this diagonal vector v plus w. But that means w plus v, we would have to slide v over to the end of w. But you can see that we're just forming a parallelogram, and so, right, going this way gives us v plus w, going that way gives us w plus v, but both of them are just the diagonal of this parallelogram. So either way, we get the same thing. That means v plus w equals w plus v, and we have our commutativity of vector addition. we could play similar games to prove all of the other vector properties. I won't drag you through all the details, but if you're unsure of any of the details, you should definitely check them for yourself. I think maybe the trickiest ones are probably distribution, although they aren't all that tricky, to be honest. So as you can see, this big list of properties that we came up with for vector spaces, it might seem like it's difficult to come up with examples of spaces that satisfy all of these properties, but in fact, lots and lots of collections satisfy these properties. Not all collections, as we'll see, but many do.